Okay, so the problem states the graph shown as a quartic function. That makes sense. You can see it's at a fourth degree and it has 3 turning points. And they've given the equation there, and they asked me to first find the equation for f prime of x. And that part should be pretty straightforward. I know that f prime of x is going to be equal to 12x to the third minus 156 x squared plus 600x minus 672. And then, so we've got that derivative, and anywhere where that derivative is 0 is going to be where there's a turning point on the graph. And it looks like I can actually see them. It looks like it's going to be at 2, looks like it's going to be at 4, and it looks like it's going to be at 7. And they asked me to factor out all 3 linear factors. Well, now you could put that into the calculator and ask it to simplify in the algebra section. But there's a couple things I already know here. I'm going to do it manually out. I know that in f prime of x, this is another way of writing the same equation. I know that 12 is a factor in each of those. So if I can factor out a 12, and I'm left with x cubed minus 13x squared plus 50x plus 50x minus 56. I've already factored those on out, so I know what this would look like as a set of factors. You could have also just put that on in and ask it to find the zeros for you, and that would factor it. But I know this is equal to 12 comma x minus 2, x minus 4, and x minus 7, because the value, any of those 3, where x is equal to 2, 4, or 7, will cause the entire equation to be equal to 0. It says the values of x in problem 1 determine the critical points of the graph of f. On this number line, put a short vertical arrow pointing down to each of these x values and write 0 above that arrow. So at 2, oh, I moved the page. Sorry about that. Let's erase that. So at 2, 4, and 7, I've drawn a little arrow. It's hard to write on this screen, and I've written a 0 on each of those spots right there. The arrows in problem 2 divide the number line into 4 intervals. In the f prime of x row, for each interval, put a plus if f prime is positive or minus if f prime is negative. We're just going to look at the original graph and look at the slopes. All the slopes in this region are negative. All the slopes in this region are positive. Not the values, the slopes. All the slopes in this region are negative, and all the slopes in this region are positive. So on the graph, I'm going to fill in negative, positive, negative, positive. And from there, on the actual graph, I'll show what's going on. This is, ooh, who wrote that? Decreasing, increasing, decreasing, increasing. Now, as we talked about yesterday, anywhere on a graph where there's a critical point, where the derivative is 0, and the graph goes from negative to positive is going to be a min, and anywhere where it goes from positive to negative is going to be a max. I'm going to fill those words on in. I should be writing them even with the f of x, but it's very hard to do so on here. So I'll scroll back to here, and that makes sense. This was a minimum point. This was a maximum point. Local mins and maxes. This is a local minimum point. And this happens to be a global min. It's the lowest point on the graph because the graph goes up and down forever. Okay, so we've taken care of that. Let's now take a look at number 5. It says find an equation for f double prime of x, the second derivative. So I'm going to take the derivative of the first equation, the unsimplified version of it, because otherwise it would be too hard to do. And it's going to be f double prime of x equals, and I'm going to take it based on this equation right here. I'm glad to see that negative 672 is going to go away. F double prime of x is going to be equal to 36 x squared minus 312x plus 600. If you put that into your solver, set it equal to 0, or ask to find the zeros on the graph, it's going to give you the two values of x, where x is equal to 0. You wouldn't have to algebraically solve this out because it's not going to give an even answer. So in the solver, you could put, like I said, that equation, set it equal to 0. And the two x values where this is equal to 0 are at 2.88 and at, lost my point, sorry, at 2.88 and 5.78. Are the two values where the second derivative is 0. So on this graph, I'm going to come to 2.88, 2.88, and I'm going to make second derivative 0, and I'm going to go to 5.7, right? Yeah, 5.78. 5.78, right about there. Don't have to be perfect. I'm going to put a second derivative of 0 right there. And then what I can do is I can look at the concavity on either side of it. Before that it was concave up, and here it was concave down, and here it was concave up. Let's just double check. Come back to my original graph. And between 2.7, yeah, it's right about there, 2.78 and 5.7 something. Oop. It looks like the graph before that is concave. This looks concave up. Happy. This looks concave down. This looks concave up. So on my chart, I could fill those in, and I know the derivative, second derivative here would be positive, negative, and positive. And now based on the math, I can say that these are both POIs, points of inflection, because the graph changed from concave, it changed concavity. The derivative was 0 there, so the second derivative changed from plus to minus, therefore it has to be a point of inflection. So I wrote POI. They asked us to write PI. I'm going to go with POI. I like that better. Okay, so how do we use this information to draw ourselves a graph? Now, the good thing about this is there's an infinite number of correct answers, but there's some things that we can do right or wrong. So let's see what they're going to give me. They're going to give me two sets of information, and I'm going to fill in what I know. Well, I'm going to look down at the first one, which is a first derivative graph. When the first derivative is positive, I know the graph is increasing. I know the graph right here is also increasing, and I know the graph right here is decreasing, and I know the graph right here is increasing. I know they're continuous functions. So, is 2 a max or a min? Well, it's not, because it didn't change from positive to negative. That must mean it is some sort of plateau. The next graph went from increasing to decreasing, so that would be a max. And this one also went from decreasing to increasing. That was undefined at that value. It's going to be a min, but because it's undefined, I'm probably going to end up with a cusp. So let's go to the second derivative right here. We have a negative derivative, so I'm going to say it's concave down, concave up. This is concave down, and this is concave down. How many points of inflection do I have? Well, the concavity changed at 2. Okay, so at 2, we have a point of inflection because the concavity changed. At point 4, we have a point of inflection because the concavity changed. And at 7, we do not have a point of inflection because the concavity did not change. First derivative tells us about direction. And second derivative tells us about concavity. So how are we going to graph all this? Well, we're going to divide the graph up into some regions. And we're going to put some dashed lines on there. I think it makes it easier when we first do the problems. So what I'm going to do is, at all my critical points and all my possible points of inflection, I'm going to put a dashed line. I'm going to put one at 2. And sometimes these match up and sometimes they don't. I'm going to put one at 4. I'm going to put one at 5. I'm going to put 1 at 7. I know there's going to be points there. I can start by picking a point in the interval. Whatever point you pick is fine. These derivatives will give an unlimited number of graphs, but I'm going to pick a point in the interval right here. And I'm going to read. Up until 2, what do I know about the graph? It should be increasing and concave down. So I know I'm going up, but it's got to have a frowny face to it. So I'm going up, and it's going to have a frowny face like so. Guess where? Anywhere I go to is fine. I know I'm at that point there. At 2, I have a plateau and a point of inflection. The graph is still going to increase, and it's going to be concave up. So it's still increasing. When I get to the next interval, I know I'm going to be at a point higher. And I want to be concave up, so I'm going to change the shape like so. I know it's not the best plateau. It doesn't have to be perfect, but that's what it's going to look like until I get to 4. I probably should have made this graph a little smaller. After 4, between 4 and 5, what happens? Between 4 and 5, it's still increasing, but it's concave down. Still increasing, but concave down. So it's going to go higher. It's going to go concave down. And I know that at that point, at 5, it's going to have a maximum. So I know it's going to start to decrease after 5 and be concave down. So all the way to 6, it's going to be decreasing and concave down. I'm going to pick a point below where I was, make it concave down until we get to there. And then now it's going to be undefined. And now the graph is going to be increasing and concave down. So I'm going to make my values go up, but concave down. And look, there's my cusp that we talked about before. We're going to do practice on working on these. Hope you did your best. I'm going to give you one more problem to work on for homework.